Hi guys, Justin again from chemistrynotes.com, and this is video number 2 from section 17. Section 17 is electrochemistry, and so far we've kind of introduced an electrochemical cell, which we call a galvanic cell. We've talked about separating the reduction and the oxidation into separate compartments. And those compartments are called anode, where the oxidation occurs, and cathode is where reduction occurs. And electrons flow from anode to cathode when we have a galvanic cell setup. So we also talked about that the voltage across the wire it's measured in volts, of course, and we want to know, and we call that the cell potential. We want to know, how do we calculate cell potentials? And that's what this video focuses on. So at the top of page 1 of our notes today, it says, so how do we calculate these cell potentials that we learned about in video number 1? Well, cell potentials have the symbol cursive, like a cursive capital E cell. And in order to calculate cell potential, we have to consider the standard reduction potentials for each half reaction. Standard reduction potentials are called Ecell with that little degree sign. That little degree sign means that we are at 25 degrees Celsius and 1 atm pressure. Values for standard reduction potentials are listed in a table in the back of your textbook. I'm also going to put our table, table 17.1, on the next page. There's no reason or no way to really memorize these. These are tables. It's like an appendix. It's supplied to you most of the time, if not all the time, and you just use it as like a reference. So just a note here on standard reduction potentials. Note, if the half reaction is reversed in table 17.1, in other words, if it's in standard oxidation potential, well, you have to change the sign, plus or minus, of E. But if the half reaction is multiplied through by an integer, the value of E stays the same. The value of this voltage stays the same. Remember, with delta H and delta G, if we multiplied an equation through, we multiply delta G or delta H through by the same coefficient. We don't do that with voltages. So table 17.1, okay, I'm going to cut and paste it here for you below. There's no way to really go over all of it. We just have to recognize that every single one of these is written as a reduction. So anytime you're presented with a question or a problem and you have a half reaction that's a reduction and a half reaction that's oxidation, you're going to have to flip one of them. Okay? So just by definition, this is called a standard reduction potential table. So every one of these is written as a reduction. Remember, reduction is gain, right? Rig. That's why you see plus electron, plus 2 electron, always as a reactant, because we're trying to gain electrons. Okay? So the voltages are listed in the right-hand column, and in the left-hand column is the half reaction itself. Okay, so we will always have that at the ready. We can have that table whenever we need it. All right? So sample problem, or an example, if you will. Top of a new page of notes here, page 3 of today's notes actually, it says, why is the voltage 1.10 volts in the redox reaction occurring in the galvanic cell below? So I'm going to sketch my galvanic cell. Whenever I'm doing a sketch of a galvanic cell, I always put my anode on the left. That's where oxidation occurs. I always put my cathode on the right. That's where reduction occurs. And I am aware that electrons flow from anode to cathode, which is why you see my electrons flowing up and over to the right. So zinc is my electrode on the left. Copper solid is my electrode on the right. I have my zinc 2+. Remember, this is all given. I'm just writing down what's given. This is the galvanic cell below presented in the problem to us. So we've got our anode, our cathode, and if we look in the anode compartment, we see zinc solid and zinc 2+. If we look in the cathode department on the right-hand side, we see Cu solid and Cu2+. So the overall equation becomes zinc solid plus Cu2 plus yields copper solid plus zinc 2 plus. How did I get that? Well, oxidation occurs in the anode. So zinc has to go to zinc 2 plus, oil. And then in the cathode, copper 2 plus and copper solid, well, cathode is where reduction occurs, Rig, so I have to get my other half reaction that way. Anode, where oxidation occurs, so this is my oxidation half reaction. Zinc yields zinc 2 plus plus 2 electrons. I looked that up in the table, and the reduction potential is plus 0.76 volts. Cathode, where my reduction occurs, the half reaction there, Cu2 plus plus 2 electrons yields Cu solid. And that one has a plus 0.34 volts. All right, so plus 0.34 volts for my oxidation half reaction. I had to look that one up as a reduction and flip it, okay? So overall, my cell potential is the potential of the half reaction for zinc and the potential for the half reaction for copper 2 plus. So my cell potential, Ecell, is equal to 0.76 plus 0.34, 1.10 volts. All right? So when I looked up the standard reduction potentials in table 17.1, I had to flip one of those, and that was the 0.34. It was a minus. I used it as an oxidation, so it becomes a plus 0.34. Next sample problem. Calculate the overall cell potential of the following reaction. Here is the cell reaction. Copper solid plus 2 moles of Fe3 plus yields Cu2 plus 2 moles of Fe2 plus. Okay, so that is my overall reaction. So if I look at the left and look at the right, I should be able to pick out who's getting reduced and who's getting oxidized, right? So there's a little star there. It says break these up into half reactions. So the first one I saw was, you can do either one first. I saw Cu solid going to Cu2 plus 2 electrons. So the cell potential for that is negative 0.34 volts. And then the other one I see is 2 Fe3 plus going to 2 Fe2 plus. And I've got 2 electrons for that one. So if I look these guys up in table 17.1, I get negative 0.34 volts for my copper oxidation, and I get 0.77 volts for my, the copper for, and I get 0.77 volts for my Fe3 plus to Fe2 plus reduction. Okay, put a line underneath everything, cross out the 2 electrons, add up my cell potentials, I get a cell potential of positive 0.43 volts. All right, so I want to introduce something to you called line notation. Line notation is kind of just how it sounds. I'm going to write stuff out in a line, but what does it describe? It basically completely describes the entire sketch about galvanic cell. You can see how sketching out a galvanic cell can get kind of tedious, cumbersome, repetitive. Okay, so it's very easy to just synopse what's happening by doing something called line notation. Line notation. When describing an electrochemical cell, in other words, a galvanic cell, line notation is used. Maybe I'll say line notation can be used. I still like sketching out the galvanic cell. I'm a visual person. I like the way things look. But line notation is also fairly visual. So I put a box around line notation. Let's read those 2 bullet points. The anode compartment is listed on the left, cathode compartment listed on the right. Sounds familiar, right? That's how my galvanic cell is set up. Let's use an example that we have done already, where I had a sketch of the galvanic cell, the 2 compartments, the salt bridge, and all that. And then let's put that into line notation. So it says, in the previous example we had from a while back, we had, if you remember, zinc solid plus Cu2 plus went to zinc 2 plus Cu solid. Remember that one? Well, in line notation, let's put that entire galvanic cell setup just into a nice little kind of linear notation. Well, on the left is my anode, right? That's where oxidation occurs. So I have zinc solid and I have zinc 2 plus. Then I have two vertical lines. That is my compartment change. Imagine that being kind of like where your salt bridge is. Then I have copper solid on the right-hand side along with my solution of Cu2 plus. So the compartment divider is the double vertical lines, and zinc solid, it's my actual electrode, right? The little dark rectangles I sketched like that. That's zinc solid. Far left, it's my anode. Far right, you can see, by the way, is copper solid. That will be my cathode. And these vertical lines that separate zinc solid from zinc 2 plus, for example, and also separates Cu solid from Cu2 plus, those are phase boundaries. Those are phase differences. That's kind of like where the solution is exposed to the electrode that is soaked in it, okay? So it's a very kind of complete way of writing the way a galvanic cell is going to look. All right, so the top of our next page of notes here, it says more examples on how to completely describe a galvanic cell. All right, so in our next video, which is going to be section 17, right, electrochemistry, section 17, video number 3, that we are going to do 3 examples, 3 sample problems that are very detailed, and 3 sample problems that are asking us to completely describe a galvanic cell. And that video is coming up right now, so stick around to see that.